I'm from Institute for Remote Sensing Applications, Chinese Academy of Science. My name is Kai Chang Di. I'm representing the three co-authors, four co-authors. The first two are my students. Third one is my colleague. As you know, remote sensing technology has been mainly applied in Earth observation applications. What our group is doing is to use remote sensing technology to do some lunar and Mars mapping applications. And as you know, these are the outlines. I'll just skip. For lunar or Mars mapping, there are usually two kinds of missions. One is the orbital mission. We use a satellite to do reconnaissance of the planet, and then usually send a rover to some interested landing sites. For example, this is the Mars rover Spirit. We have two kinds of images, orbital image and ground stereo images. As you know, in order to do science and engineering, we need a 3D model of the terrain, just like we did on Earth. So we wanted to build a 3D model from this orbital and ground images. 3D mapping heavily depends on the image matching technologies. As you know, image matching has been intensively researched in computer vision and photogrammetry, and particularly global image matching has been proposed for global optimization for the overall result. We want to test these methods and develop some new methods to lunar and Mars images, because relatively the global image matching is not fully tested for lunar and Mars images. The images looks different, right, from the Earth observation image. This is a mosaic of ground images taken by Spirit rover. You see there are a lot of rocks, hills, and generally the surface is quite monotonous. That means there's not much texture. So sometimes it's challenging to build a dense 3D model from these images. This is a lunar orbital image. It's a mosaic from China's Chang'e 1 lunar orbiter. The resolution is 120 meter per pixel. This is the stereo image of an area called Sinus Aridum. In Latin words, the Bay of Rainbows. This will be a landing site for China's Chang'e 3 lunar rover. Recently, we have a Chang'e 2 mission. It's also an orbiter with a resolution of 7 meter, full coverage of lunar surface. So we want to build 3D models from these images as well. Here is our strategy. Basically, we have good features. We use a interest point extraction method like Forstner or Harris. So we extract and match these reliable features first, and then use some ransack strategy to detect gross errors or outliers. Then we generate a chain, triangulated irregular network. We build this chain as a control. So these information reach points are reliable. So based on this, we do disparity prediction. Then after that, we use a Markov random field model to model the whole parallax surface. Then we do energy minimization procedure to get a global optimization of this parallax surface. Then we apply a least square matching to get a better geometric accuracy to reach subpixel accuracy. This is the overall procedure. A little bit detail on the steps. First step is feature matching. We use the famous Forstner operator. Then we do left red consistent check, and then we use a ransack procedure. I use a similarity transformation model to detect outliers. After that, we have some new development in this part. We use a feature point constraint Markov random field. Usually in the previous study, Markov random field is just initially from just given a zero parallax and start from there. Now we have pretty good initial result from this interest point. Then we start from there. We increase the reliability and also reduce time. So basically, it's an entity function. For each point, we have a data atom, which can be the correlation coefficient, and then there's a smooth atom to consider the neighbors. So the consistency with the neighbors. So even if the texture is low, but with the constraint from your neighbors, you usually get a better results. These are the atoms of this entity function. Due to the time limit, I won't go to the detail, but the idea is not only consider the point itself, but also consider the neighbors. If we do not use this MRF model constrained by feature points, this is a triangle, so we are already met this. We can predict what the parallax would be for this center pixel. Also, we consider the surrounding features. Then, originally, if we don't have this feature information, then for each column and row, for each pixel, we will have a disparity search range. So this will be a 3D cube for each pixel. Then after this prediction, we will only constrain the search range with some discrete ranges. This reduce time and improve reliability. Here are some details of how this search range is defined. This is from the Tien interpolation. These are from the surrounding search range. Basically, it's a union of these search ranges. So for every pixel, we have a reliable search range. Then we do Markov random field optimization through belief BP from belief propagation. Basically, the idea is for one point, we send a message to the surrounding point, and in the iteration, the point will receive information from the surrounding points. Then we have a minimization through this process. Then after that, we will have, so this point we consider the surrounding points. Then after this iteration, it will reach a global minimization. This has a proof for a Man random field. It's a popular one. We just added some feature to constrain this random field, Markov random field. Here are some examples. This is a Mars image, stereo image taken by Security rover. It's a small feature. The rover moved very close to it and do some investigation. So we need a 3D model of it. And see, here is the immediate result. We extract a lot of features. We build the triangles first. Then we use the triangles to control the MRF optimization. Then we have a dense image parallax surface. Because on my screen it's quite clear, but because of the projector, we don't see a lot of difference. But anyway, this is our result. It's seamless, almost seamless. But this is in the middle. This we download from NASA's JPL website. This is produced from their pipeline. So you see there these dark areas are holes, so there's no parallax data. Basically, there's some areas there's no texture or there's a sudden parallax change. So in these areas, the result is not good. So in our new method, these featureless areas, because of the global optimization through the feature control. So we have a pretty good result. This is the reconstructed 3D model of that feature. You see the textures and the tiny little morphology are revealed. This is also photo overlaid on the DM, so we can see the features, can do measurements for. So scientists use this to do their geological analysis. We just provided this fundamental information. These are the channel 1 image. This is the disparity map. Here is the automatically generated DM. This is also the image overlaid on this DM. So we see these craters and the slopes are revealed quite nicely. These are just our preliminary results. Also, in order to do research for mapping and navigation, we built a model rover that integrates a stereo camera which can rotate 360 to get panoramic images. And also we have odometer and MU for navigation. So here is an example of DM generation. So at one stop, the rover take panoramic images, and our software will build a DM and a DOM automatically using our feature point controlled RMF global matching method. So generating this DM and DOM will only need about 1 minute. It's not in real time, but anyway, you will stop the rover and take the panoramic images, so it's near real time. A short conclusion. Basically, stereo image mapping is still of great importance and still interesting hot topic for 3D mapping. The proposed method looks effective and is flexible in terms of incorporating feature point and the constraints. The preliminary results are fine, but we will use more lunar and Mars images to test our new method. Hopefully this will be implemented further and applied in real missions. Thank you very much.
Thanks for Dr. Li. May we open questions to the floor?
Have you tried SIFT matching your approach?
Exactly, yeah. SIFT is a very popular detector and matching method. We tested it. It is pretty good for some images, but the advantage of SIFT is it is invariant to scale and rotation and some illumination change. But in our case, we have stereo images from rover or from orbit, so the scales are pretty consistent. And then we test it. Then usually we have more feature points, we have more matched pairs using Forstner or Harris operator than SIFT because the scale effect. But in our navigation application, actually, because the scale changes along the route, we did use SIFT matching. That have a better result. But in this case, for mapping, we didn't use that, but we tested that.
This was an interesting topic or talk. In terms of the MRF, in your diagram, you have only showed one spot, and the rest of them looks like a 3x3 arrangement. Is
Yes.
it in reality the case because MRF can handle 5x5?
Yes.
Window size? I don't know what kind of window size.
We use the traditional 3x3, but we have actually, in order to improve reliability and speed, we have hierarchical belief propagation. So basically, it's like a pyramid. So that, but the basic implementation is a 3x3.
the global match, when you reach this goal, you say the minimum is reached because you have a cost function, something like that.
Yes.
Built in. And I would like to know if this global energy minimization has something to do with all those points, feature points you showed us, and triangulated by the team.
Yes.
How many points are there? 3,500 or so?
Usually for a 1K by 1K stair pair, we have like 1,500 points, pretty dense already. So these points will play greater roles in the optimization process. Basically, they have higher weights. But still, we need to determine some parameters like the beta, the balance between the beta atom and the smoothness atom.
The third question is whether it is necessary to absolutely find points for disparity, because there is no correspondence. In some cases, it looks to me that you force your way through this stereo pair.
Yes.
Because in comparison, you show the NASA result and your disparity result.
Yes.
It looks like that you want to have a good disparity map. But my point is it necessary?
Yeah, it's a good point. Actually, in the real mission, we didn't produce. When I worked in Ohio State University, we did this navigation and mapping for NASA. So in a real mission, we need reliability, safety. So for some areas we don't have points, then we mark it as a whole. But for research, we still try, because through a 3D view by human eye, we still have a perception there's a 3D information. In research, we want to do this a little bit further. It's different. Thank you.
Any more questions? If not, then let's move to the next presenter. Thank you, Dr. Lee. I ask